Today I am going to speak on vibration of rigid bodies. In this course, we will be discussing the vibrations of single degree of freedom system. By degree of freedom is meant independent coordinates to describe the system. For example, in the previous lectures, we have discussed the vibrations of spring mass system with damping or without damping. In these systems, what happens that you have to, now we obtained only one dimensional equation. We had x. So, position of the mass or that particle is described only by x. So, independent coordinate is x, therefore, this is a single degree freedom system. If I would have kept like this, suppose there was a mass and this was the spring, another mass, then this would have become 2 degree of freedom system, because I need to tell the position of this mass, then I need to tell the position of the another mass. So, it is like that. So, a 2 degree like that we have 3 degree of system if there are 3 masses attached by springs, because I need to locate the position of 3 masses. Now, like that, if you go to say bodies, we discussed in the first lecture itself the concept of continuum, where we consider that the body is a continuous matter, mass is as a continuous, therefore, in this there are infinite number of particles actually, and as such, if the body can undergo deformation, then there are infinite degrees of freedom possible. However, we know that we are studying rigid body, and in rigid body, if we are going to study a particle is having 3 degrees of freedom, and body composed of the particle has basically 6 degrees of freedom. So, therefore, in rigid body the degrees of freedom get reduced and they become this one only 6. Now, therefore, similarly the particle, we know although the particle has 3 degrees of freedom system, when we discuss the spring mass motion, then we assume that the particle is constrained to move in one direction only, it is not moving in the other 2 directions, therefore, it has got it is 1 degree freedom, other 2 degrees are arrested. Similarly, if the body, a rigid body is there, then that rigid body can undergo 6 degree of freedom, 3 translations, the center of gravity can move in x, y and z direction, and once we fix the center of gravity, then the body can be oriented in 3 ways by theta, phi and another that angle alpha. So, therefore, it has. However, if we restrict the body to plane, then the body has only 3 degrees of freedom. A rigid body in xy plane is only having 3 degrees of freedom, because it can be moved along x, it can be moved along y, then it can be rotated about the z axis. So, if we just have the its degrees of freedom may be x c, y c, that is coordination, and plus its orientation theta. However, if we somehow constrain the motion of the body and allow it to have only 1 degree of freedom system, then such problems can also be solved in the means with this our whatever we have discussed, that means which is in the scope of that our present course. So here that it is like this, that if you have say rod, now this rod has been hinged at one point and therefore it is not able to move in x and y direction. This point is restrained, but it can rotate, so it is having a single degree of freedom. So why we cannot study the vibration of these type of things also? It may be rigid bodies, they may be undergoing this thing. So let us come to this one. So planar rigid body vibration is similar to the analysis of particle vibration. In fact, when the particle, this can be considered as a complete rigid block also, composed of so many particles, because it is going only translation and all particles are having same velocity and same acceleration, same type of displacement from if we from a particular datum. So therefore in particle vibrations the variable of interest is one of translation, while in rigid body vibrations the variable of primary concern is one of rotation theta. So you know that we just go to that this one. In the case of now when we it is of theta, so before that let me tell the concept of the torsional system, like let us quickly go to that this one. Here see, we know linear springs. In linear springs there is a spring, if you apply a force F, the spring gets deflected. Suppose this deflection is delta, then K is equal to F by delta, where K is called the spring constant and it is having the unit of Newton per meter. In torsional system, this is suppose you have a torsional spring which can be indicated by this. It is like this here, like this here, this is the spring, and if I u, suppose I fix it here, and if I apply some torque T here, then the spring gets displaced, angular displacement is there, we say T is equal to Kt times theta. Now unit of torque is equal to Newton meter, Kt, and this is radian per second. So this is what happens, the dimension of Kt, this is radian per radian only. So therefore dimension of that thing will be Newton meter. So therefore Kt will be Newton meter, right. So therefore what happens, now going back to the previous slide, we see similarly now just see that we have, let us take a rod here, now it is fixed here, with this is attached a torsional spring, so that when the rod rotates by theta, then a restoring moment is developed, that is Kt times theta. So that restoring moment will be Kt times theta, and there is this side we have kept a linear spring whose spring constant is K. Now in this case the total torque including the inertia torque is summed up to 0, that is D'Alembert principle, or we can say that we can apply the Newton's law generalized to that angular coordinates or angular degree coordinates. Then you have I d square theta by dt square plus kt theta is equal to c d theta by dt is equal to t. I d square theta by dt square is the inertia torque. d square theta by dt square is the angular acceleration with the unit of 1 by second square, and I is having the unit of mass moment of inertia, so it is kg meter square, kt is Newton meter, c is the viscous damping effect. Just like there we had c times x dot, here I am putting c times omega, that means c d theta by dt. So this must be equal to applied torque. This is the equation, I d square theta by dt square plus kt theta plus c d theta by dt. Now if t is equal to 0, then this becomes the case of free vibration and you get this thing. The equation is similar to what we have studied in a spring mass system, only theta is replacing x. So therefore this kt is called torsional spring stiffness, c is the damping factor and t is the external torque. Now so inertia moment is r minus I theta dot dot. I is the moment of inertia of the bar about the left end, and this is given by ml square by 3. You have this as you have a rod, its moment of inertia, uniform cylinder rod, its moment of inertia about this point is ml square by 3. About its CG, it is ml square by 12. So I is equal to ml square. Moment of torsional spring is minus kt times theta. Deflection of linear spring is actually L sin theta. So we have the spring like this, and if it gets displaced, this is theta, so this is L sin theta. So we get L sin theta. Therefore force is equal to minus KL sin theta. Linear spring applies a restoring force, that is minus KL sin theta. Now moment about axis of rotation is minus KL square sin theta. Because we take the rigid rod is in balance under the action of these three moments, that is moment of torsional spring, deflection of moment due to linear spring, and the inertia moment. Therefore the sum of these moments will be 0 because there is no externally applied load, that is ml cube by 3 theta double dot plus kt times theta plus kl square theta equal to 0. This is a linear equation. That means if alpha is a solution of this and beta is another solution, then c times alpha plus d times beta is also another solution. Now rewriting it, we can say ml cube by 3 theta double dot plus kt plus kl square theta. Kt is the torsional spring constant, therefore its unit is Newton meter. This is Newton per meter into L square is meter square, so dimensions match, so Newton meter Newton theta equal to 0. Now let us compare it with the equation mx double dot plus kx equal to 0. We already have solved this equation, so why solve this again? Only thing that it is m, instead of m I will put ml cube by 3, instead of k I will put kt plus kl square. So we can straightway we can get the expression for natural frequency omega under root k by m. So same way omega under root 3 kt plus kl square divided by ml square. Unit of torsion spring constant kt is Newton meter. So this is that this one. So omega is equal to kt plus kl square divided by ml square. Now if of course that k is equal to 0, that means spring is just supported at one end, by torsional spring like this, but the other end is free. In that case, omega will be cube the under root of 3 kT divided by ml square. So this is that type of thing. Similarly, if there is no torsional spring, that means this is fixed, but then kT is equal to 0 and it is supported on this spring. If k is there, then it will be 3 k under root m. So this is about this thing. Next, we will study the vibration of torsional system shown in this figure. Here what happens, in this there is a rod. Now with this rod you attach a disc. Now if you twist the disc, so this rod also gets twisted, but this end is rigidly fixed. That means this all cross sections, they rotate with respect to each other, therefore restoring moment is developed, and that expression here it is given kT. Now that can be measured experimentally also. You give a small displacement, angular displacement theta, then see how much torque is developed, and then therefore kT divided by kT will be torque divided by theta. Now in this system, if the moment of inertia of the disc is I and it is mounted at the end of a shaft without weight, that means weight of the shaft is negligible compared to the weight of the disc, and having a torsional spring constant kT, where kT is equal to T divided by theta, that is kT is the torque required to produce a unit angular deflection theta in the disc. We measure theta in terms of the radian. Okay. Consider the disc as a free body. Torque acting on the disc or inertia torque, which is equal to minus I theta double dot. Restoring torque is kT theta dot. By D'Alembert's principle, the rod has to be balanced under the action of these two forces. Therefore, hence minus I theta double dot minus kT theta double dot equal to 0, or theta double dot plus kT by I into theta equal to 0. So therefore, natural frequency, this you can compare this expression with mx dot plus kx equal to 0, and therefore omega n is natural frequency is obtained. Omega n is equal to under root kT by I. kT has the unit of Newton meter. Let us see the units here. Newton meter, kg meter square, and Newton is kg meter per second square. So you have second square, then 1 meter was already there, meter square. So meter gets cancelled, so it becomes, and this is kg, so you get 1 by s. So 1 by, so omega n means its unit is second inverse. General solution of this system is given as theta is equal to a cos square root kT by I into t plus b sin square root kT by I into t, where constants a and b can be found from the initial conditions. You can have different type of initial conditions. At the starting, the displacement is 0, then or you can have the condition at the starting you give some definite displacement and the velocity is 0. So angular velocity is 0. So this is how that it can be done. And now let us discuss the case of compound pendulum. Okay, that also can be discussed. Before that, little bit recapitulation of the simple pendulum. Simple pendulum consists of this thing, that there is a string, with that you attach a small bob so that it can be treated as a particle. The entire mass is concentrated here, and this is L. If you displace it, that there is no spring here, but if you displace it there, its potential energy rises and gravity tries to pull it to the another, this lowest position here. So at this moment there is a gravitational pull, that is mg here, and then you have got tension here. So T, this, if this angle is theta, then T cos theta is equal to mg, and T sin theta will be the component in this direction, T sin theta. T vertical component balances this, and another component is T sin theta, which is like this. So T sin theta. Now here if we take the moment about this point, then mass m, moment of inertia is ml square theta double dot is equal to minus T sin theta. Now if we assume that theta is very small, in that case T will be equal to mg and sin theta will be theta. Therefore this becomes minus mg into theta, and therefore L square theta double dot plus g by g, this is minus T sin theta. Here I have to multiply by this one length, then it will become this thing moment, this is restoring moment L. So L g theta is equal to 0. So here we get theta dot dot plus g by L theta, g by theta equal to 0, or here this system, so comparing with mx dot double dot plus kx equal to 0, we get omega n is equal to under root g by L, like that. So therefore assumption involved here is that theta is very very small. That's why we could write T cos theta is equal to, and we will be able to get the simple harmonic motion. Now discussing about compound pendulum. In compound pendulum, mass is not concentrated at one point. In fact, it is distributed. So this is the compound pendulum shown. A rigid body having angular oscillation about a point of suspension is called a compound pendulum. Here the mass acts through the center of gravity, and these are the another this. Let G be the center of gravity and O the point of suspension, and if I0 is the moment of inertia of the body about O, you have a pendulum like this. So here in this case you have to take moment of inertia about this point. This is O and this point is G. G is the mass. Now if you displace, if OG gets displaced by an angle theta, then you get restoring torque minus W times OG theta, because the angle is small. So here you have W and this point gets displaced, this weight is there and this gets displaced by this one. So it is like this rises here. So therefore you get a restoring torque as W times OG theta, just like you got in simple pendulum. Theta is assumed to be small, hence I theta double dot is equal to minus W OG theta, where I is basically about, I should write it I0, that means it is about a point O which is suspended here. Therefore I is the moment of inertia of the pendulum about O, thus IO theta double dot plus WOG theta equal to 0. Again compare it with mx double dot plus kx is equal to 0. We see that omega comes out to be omega n WOG, this is I0 WOG, and this can be written as W by G. W by G is basically mass times K square, where K is the radius of gyration. This is radius of gyration about point O. This is equal to OG times G divided by K square. Now when we know that the natural frequency of a simple pendulum is square root G by L, comparing this with the natural frequency of the compound pendulum, we can say that the effective length LE of the compound pendulum is given by LE is equal to K square by OG. So because here in this expression, this is compare it with under root G LE, therefore LE square, LE is K square by OG. In this expression, K square is the radius of gyration about fixed point O, which is equal to kg square plus OG square. This comes from the parallel axis theorem. K square is equal to kg square plus OG square, where kg is the radius of gyration about G. Therefore LE is equal to kg square plus OG square divided by OG. This comes out to be kg square by OG plus OG. Now if you have a compound pendulum like this, and here this point is extended up to C, some point C, where OC is equal to OG plus kg square by OG. That means GC is equal to K by OG. GC is equal to kg square by OG. Then C is called the center of percussion. We have already discussed about center of percussion in the previous lecture, and LE comes out to be OC. That is, the equivalent length is equal to the distance from fixed point O to center of percussion. Center of percussion is the point that about, if you strike at that point, then no reaction is developed in the direction of the striking of that force. So that means, so this is the thing. If you know the center of percussion of this one body, then you can apply a tangential force here. It will not produce any reaction in this direction. That we have discussed in one of the previous lectures. So this is about that. Now we will discuss about other problem. If a body, we discussed bifilar suspension. If a body is suspended from two strings and given an angular displacement theta about the vertical axis and release, it will execute torsional vibration. Such an arrangement is called bifilar suspension. That in this one, that it is figure, I am drawing the figure here, that is a bifilar suspension will be like this. Here this one, and it is a disc type of thing. Here it is, you have string here attached, string is attached here. So this is the G and this is C, this is D, then you have L, this is L. Now this arrangement is called bifilar suspension. It is suspending like this. If I twist it disc little bit, if I give that twist here, then allosteric moment is developed. Why? Because these strings which are vertical now, they will be also twisted by the same amount and they will become inclined. These inclined strings will provide vertical as well as horizontal component. Vertical component will support the weight of the disc, whereas the horizontal component will provide the restoring torque. So if we give a small angular displacement theta to the disc in its plane, the string holding the disc will become inclined. Now inclined strings will provide horizontal component of the force due to their tensions. The tension in strings attached at C and D respectively will be like this, that here if it is C and it is D, so in C it will be WGD divided by CD, then this is WGC divided by CD, this is TD, this is TC, WC. So this is, because this is that angle theta, so that theta will become like this. If you say that theta, that is, so this rotates little bit, so that is L. Suppose you have here attached the string like this, and this is thing here, that G, and this becomes theta. So this will be equal to that r theta. Suppose you give that displacement r theta, and this is the height is this one. So it is basically r theta, and this phi is equal to, basically it will be r theta divided by L. So you will have r theta divided by L type of thing. This is like that. So W GD by TC is equal to this one. For small angle of rotation, we can always write CG times theta is equal to L phi C, if we say angular displacement phi C, and GD times theta is equal to L phi D, where L is the length of the string, and this is from the, and angles are like this. Here this is phi c, like that, phi c. So therefore phi c is equal to cg times theta divided by L, and phi d is equal to gd times theta divided by L, and this will be equal to, then the horizontal component of forces due to 2 will be Tc phi c, and that same thing will be and this is Td phi d, and these will be Gd times Cg theta Cd by L. Only for small theta, Tc phi c and Td phi d are components of tension in the horizontal direction. Now taking moment about the center of disc G, we obtain the restoring moment. So restoring moment will be Tc into phi c multiplied by Cg plus Td into phi d multiplied by Gd. Therefore this will be equal to Tc times phi c Cg plus Gd, or it will be Tc times phi c multiplied by Cd, where Cd is the distance between these 2 points. So this is Cd. So this is like that. Now therefore the equation of motion is given by Ig theta double dot plus W Gd into Cg theta divided by L into 0. So this is that Ig theta double dot plus W times Gd Cg theta L, and therefore you can have, comparing it with the simple spring mass system, the natural frequency is given by omega n is equal to W Gd Cg and divided by L into Ig. L is the length of this thing. So this way that we can find out the frequency, natural frequency of this suspension also. So this is the thing is this one, and then I will be now doing that some simple problems for this system. Now here let us go to that one. Let us try to solve that some other problems. Here if there is a pivot, here one rod is fixed here. At the end of the rod I took two small balls and their masses may be m. This is equal, same, actually it is equal, this is the thing, and then here you attach, this is the upper, that force one guide, and here another fixed wall, and here you attach a spring like this, and attach like this, attach like this. Assume that this figure I have drawn is in a horizontal plane, so gravity effects are not there and it is in a horizontal plane, so it vibrates. Now what will happen, that when we rotate it about this hinge point, then restoring moment is developed. There is a spring K, let us say spring constant is K, this spring constant is K, this is also K, this is also K. Now if you give a small angle theta, then there is a rotation. Now this is, let us say that this is L, and this will be L. Now if you give a small rotation theta, this point, this ball gets upward by an amount L theta. So this spring gets compressed by amount K theta, another spring gets stressed by K theta. Therefore they apply the forces and this will be K theta. So total force coming on this ball will be basically 2K theta. Why? Because this spring gets compressed by amount L theta, KL theta. This is KL theta. Another also gets stressed by KL theta. So both are putting the forces in the same direction. They get added up, and this is 2KL theta. In fact, these two springs are in parallel. Similarly, this side also, this spring gets compressed and this gets stretched. Compressed spring puts force like this, stretched spring tries to pull it upward, and therefore again this force is 2KL theta. Now this is 2KL theta, this is this one, and then take the moment about the pivot point is O. So we have to see that what is the total mass moment of inertia about point O. This is mL square plus mL square, that means 2mL square. Now you apply that equation, 2mL square into theta inertia torque is equal to plus, you will say 2KL theta. This is actually a couple, 2KL theta acting there, and the distance between them is 2L. So 2KL theta 2KL theta into L, that means 2KL L theta equal to 0. That means mL square theta dot dot plus KL square theta equal to 0, or theta square gets cancelled. So therefore this is 2. Therefore theta equal to theta plus 2km, take 2kl by theta, 2kl 2km theta equal to 0, or omega n in of this system is given by under root 2k by m. So this is how that you know that this rigid rod will vibrate. Okay, let us try to do that another problem on this system. Here this is rod if I take a thin laminar here, if there is a hinge here and you suspend it like this, and if it starts vibrating about AA, give a small rotation about AA, and if this length is B, this is B, then we are interested to know that what is the frequency of oscillation or what is the time period. So when it starts oscillation about axis AA, then we have to find out the moment of inertia about axis AA, and that is given by mb square by 3 into theta this is about this one theta dot. mb square by 3 is the moment of inertia about AA, and this gets displaced. Its CG is at a distance of b by 2, and when it gets displaced by an angle theta, then you get the restoring torque equal to minus b by 2 m g theta. This is the thing. Therefore, this becomes b square by 3 theta plus b by 2 g theta minus mg theta into b by 2 is the distance. So that torque, because if I make this side view there, it is like this gets used theta. So what happens that this is b by 2, this distance is b by 2, and this is b by 2 is the distance and this mass. So this is mass mg. So that one component is basically, it's a component along, this is mg, that tension. So tension T is equal to mg for small angle, and its component is mg sin theta. So you get is equal to 0, and therefore omega comes out to be equal to 3 by 2 g by b. So we get this type of thing, omega is equal to 3 by 2 g by b, and time period t comes out to be 2 pi by omega, that means 2 pi under root 2 by 3 b j by b by g, and this is the solution of this problem. So this is how that it can be done. And now one problem on compound pendulum. Now a compound pendulum is shown here. This point is O1, this point is G, this point is R1, and from here to here another one point is I have marked as O2, and this distance is R2. In this problem, it is given that K0 KO is the radius of gyration about O1. Now it is given that if this compound pendulum is hinged at O1 and then oscillated, you get certain time period. If the compound pendulum is now hinged at O2 and provided oscillation, then you get time period. Both time periods are equal. In that case, what is the relation between the radius of gyration K, KO, which KO is the radius of gyration about point O1 and R1 R2. So let us try to solve this problem. Let us go back to the compound pendulum slide. Compound pendulum, we have got this is thing LE is equal to K square divided by OG. So effective length of the compound pendulum is given by K square by OG, and that means OG into G divided by K square. So this is the same type of thing we have to put here. So this is 2K. So therefore time period of the compound pendulum is, since time period is same, therefore angular omega will be same. Therefore what we will be writing, that K square, now let me use the expression for this thing, equivalent length is K square OG omega n is equal to OG, we had OG multiplied by G, this is K square. So that same thing here, that for the first case it is R1 multiplied by G, R1 multiplied by G, and then divide by K square, K0 square is equal to, now about this I will be writing K0 square, this is R2G, GR2, and this is K0 square. Now I am suspending about O2. So therefore this will be K0 square minus R1 square plus R2 square, because the radius of gyration about G is now K0 square minus R1 square plus I am putting that R2 square, because I have to find out radius of gyration about this one. So therefore we get a relation, basically K0 square by R1 inverse this. So this must be equal to K0 square minus R1 square plus R2 square divided by R2. This can be simplified as K0 square divided by R1 is equal to K2 square, K0 square by R2 minus R1 by R2 plus R2. This can be written as, this is minus R1 square, should be dimensionally balanced through K0. So therefore this can be written as K0 square, R1 R2 can be taken as common, this is R2 minus R1 is equal to, this is minus R1 by R2 minus R1 square by R2 plus R2, or you take 1 by R2 common and you take R2 common here also, this is 1 by R2, and this will be minus R1 square by R2. This is R2 by R1. So when you simplify this expression, I am now skipping 1 or 2 steps, then you should get K square is equal to R1 R2, which is the required that relation. So K square is equal to R1 R2. So you have been able to solve this problem also. So this is what that happens about this. Now so we have discussed about that. So in this lecture, let us summarize what we have talked. We have seen that when a rigid body is constrained to move in a particular way, so that its position can be described by a single coordinate. It may be the angular position theta, then it becomes a single degree of freedom problem, and it can be solved in the same way as the spring mass system. So the differential equation remains basically same. Therefore mathematics required is basically same. So we have discussed about this type of motion. So first we took up the case in which a torsional spring was put, and after that we have discussed the case of a disc fixed by suspended from a rod or shaft. This is the thing. So when we twist it, the shaft gets twisted, and due to elasticity it tries to come back to its position, and therefore it has some equivalent stiffness. That case also we have discussed. Then we have discussed about the compound pendulum problem, which can also provide simple harmonic motion. However, now its omega n will be basically under root instead of G by L, this will G by LE, where LE is the equivalent length, which is the distance from the its a fixed point up to the center of percussion. So this is what we have discussed. Equivalent length is equal to the distance from fixed point O to center of percussion, and this is this we have discussed. Then we have done simple problem, like one problem we did bifilar suspension. Here there is a disc which is suspended by the two strings like this, and then it is given some twisting. So in that case, what happens, that type of motion we have studied. Now in the next lecture we will discuss more about the vibration of rigid bodies. We will first start our discussion with a trifilar suspension, where there is a same disc, but it is now fixed from a ceiling by 3 strings. So one string may be this, another may be here, and the third is here, like that. So this is fixed by this thing, that is called trifilar suspension. We will discuss start our discussion from this in the next lecture.